Okay, so let's see here, double check. Okay, we're recording. So here's where we left off from last time. We've been talking about double integrals and iterated integrals and stuff like that. The thing is that every question we've considered so far, the domain, let's see if I can find it. Here we go, nice picture. The domain has been a rectangle. For every domain, for every application we've considered so far, every integral we've considered so far. Okay, so what we're going to do now is consider how do things change if the domain's not a rectangle. Now, first of all, why would we ever care if the domain's not a rectangle? And, well, for extremely natural reasons. And just as an example, not even the most persuasive example, of course, but the easiest to visualize. If you're interested in the volume question, you want to find the volume under a surface over blah, blah. Well, I mean, it could totally be that you just very well might want to compute the volume sitting over some wacky shape like this. Maybe your loaf of bread doesn't have a rectangular footprint, right? Of course it might not. In some sense, the idea that we would ever the only domain over which we would want to add stuff up would be a rectangle. It's silly, right? So we really do need to consider this question of what do you do if the domain's not a rectangle? And here's the good news. It's almost all exactly the same. Almost all of it. Practically everything is exactly the same. Again, easiest to visualize with the volume question. So computing the volume of this loaf of bread, well, we still are going to slice it up into slices of bread. Some of them are going to be thinner this time. Some of them are going to be wider this time. But still, the whole is the sum of the parts. I mean, again, that's how volume works, right? It's got nothing to do with the shape of the domain. Okay, likewise, again, this piece of volume is a cross-sectional area times a thickness. It remains that cross-sectional area is still itself the area under a curve. That curve is still a graph. It's still a graph of what you get when you fix y, right? Everything's the same. Practically everything. The only thing that's different is as follows. This integral that we use to compute that area. If we look at the bounds, where does x start and where does x end? Those are now going to depend on y. That's it. That's the only difference. Simple as that. Those inside bounds are going to depend on y. Now, let me walk you through why that is. Zooming in so we can see better. Looking at this picture here. For, let's say, this value of y, we notice that this point here, in some sense, is where we start with our x integral to compute that cross-sectional area, right? And that point gives rise to this x-coordinate as our lower bound for x. But now just look at the picture and think about a different value of y. What if we were looking at this value of y right here? Right? Y is going to take on all of the values between c and d. And for that value of y, pretty easy to look at the picture and see that point on that same curve, mind you, is the one that will determine the lower bound for x, right? In fact, you can even draw what your little y slice is going to look like there. There's going to be a tall, skinny slice of bread there, right? And so we're going to correspondingly then get a different value of x as our lower bound. Let's see, did I have the foresight? No, I didn't. Okay, well, let me redraw this. That gave us that value of x. This other one gives us that value of x. So different y's give you different x's. Said differently, x is a function of y. Okay, and so you can see that right here in the bounds. Our x bounds now depend on y, aka they're functions of y. That's the only thing it changes. Everything else is the same. Real quick comment, there's also the question of, okay, keeping in mind that we agreed that that iterated integrals have pretty limited use. The only reason we really like iterated integrals is it interfaces nicely with the volume question. That's satisfying. And it's computationally convenient, right? But there's this other big looming question of what about double integrals over a non-rectangular domain? How would we define that? And even better answer. The only difference between non-rectangular domains and rectangular domains are little formalities that are not the purpose of this course. So morally, and again, intuitively, the big picture, when you're thinking about a double integral, and let me go back to where we have a picture. Here's a pretty good picture. Let's visualize it this way. When you're taking your domain and chopping it up into little pieces, if it's not rectangular, well, you're going to have a different collection of pieces over which you're going to do the exact same construction, and how to formalize that, and how do you define your delta x and your xi, and so that's again, not our problem. That's more of a real analysis thing. And I'm going to say, as far as we're concerned, practical purposes, it's exactly the same. Don't worry about it. Okay. All right. So, now, last observation I'll make about this picture, at least for the moment, is to notice that the way we found these bounds, the way I found that lower bound, A, as a function of y, and this upper bound, B, as a function of y, is by looking at this three-dimensional picture. But notice the height didn't come up at all. The only role that height plays in this picture, the three-dimensional part of this picture here, its job is exclusively to give us the integrand, right? All the questions about the bounds all take place down here in the domain, right? So all of this bound stuff that we're interested in, how do I find that bound? How do I find that bound? I'm just looking just in the domain. That's two-dimensional. Two-dimensional is a lot easier to draw. This three-dimensional picture is pretty hard, right? It's pretty tricky artistically and challenging. And why would I throw myself a nasty artistic challenge when I don't have to, right? So this little game that I argued about, okay, well, for a given value of y, you find the corresponding point that's on some curve, and then use that curve to figure out how x is a function of y. That all happens in two dimensions. Let's see it in two dimensions. Just as good. I can't see the height. This is sort of, if you will, as seen from above, right? This is the bird's eye view of, looking straight at satellite view, I guess these days, looking straight down on this region. Don't see the height, don't need the height. So, same scenario. How does x depend on y? Well, first, we recognize that y goes from C to D, and then we pick a value of y to look at. We look only at that y slice. Now, that's, again, as seen from above, that's, I've got to clean up my mess here. That is, as seen from above, this slice there. Yeah, sure, fine, I suppose, if you want. But as far as we're concerned in finding the bounds, I don't need to see it from above. Let's just look and see just this little slice of the domain. Forget about the loaf of bread. Right? And then let's see here. Okay, so what is my starting function? Looking at my range of x going from sort of there to there. In other words, x as seen on the x-axis going from there to there. I look at this point on that curve to solve for that lower bound for x. And I look at this point on that curve to solve for this upper bound for x. And now again, that's exactly what I did in this picture up here. Just hard three-dimensional picture, abandoned, and now much easier to draw, much easier to visualize two-dimensional picture just as good for finding these inner bounds. So please do remember the process, though. You need to identify which bound are you looking for. Think very carefully. Don't try to do your lower bound and your upper bound at the same time. Be clear in your mind, which bound are you looking for? What is the corresponding point, right? Like this one or that one, depending, that defines that bound. What curve is it on? What are the equations of those curves? And then just solve for what you want. Nice, simple process. Let me show you how this works in practice. Okay, so looking at this example right here, our domain is this triangle. Right there. We want to compute some double integral on that domain. Now, real quick side note, why do we want to compute that double integral? Who knows? Lots of possibilities. Maybe I'm computing the volume and this is the footprint. Maybe I'm computing the population of this weird shaped county somewhere in Idaho or whatever. Right? Maybe I want to compute the amount of mass that's distributed over this shape for whatever reason. Millions of applications. We don't need to worry about that part right now. We're presuming that whatever the application is, this is the corresponding double integral. All we're going to focus on right now is how to turn that double integral into an iterated integral. So don't worry about the application. So that said, with that being the domain, how do I slice this up? And I've got a couple of options. My first option here, I'm going to slice first in the x direction. And you can see I've got x going from 0 to 1 right there in my development of my iterated integral. Now, with that decided, we're going to fix a value of x. And now for that value of x, I look at this x slice. And let's see here. Let's start with the lower bound. Lower bound's determined by that point. That's kind of the starting point as I move in the y direction. That point is on this curve. That curve has that equation. Solve for the variable I'm interested in. I'm looking now, if you'll notice, for a y bound because I'm going to imagine y going from start to finish. So this is the start of a range of values for y. So solve for y in this equation, and in this case, it's easy to solve for y. Y is clearly 0. That was an easy little starter. Let's think now about the next case. Let's look at the upper bound. The last value of y, again, as y ranges over my x slice. That point is on that curve, which has that equation. Now, real quick, side note, how do I know that that's the equation? That wasn't given. The equation wasn't given. Where did I just pull this out of thin air? Where did I get y equals x? Okay, true, but I was given these 2 points there, and that does allow me to do a little bit of, high school algebra, geometry, whatever you want to call it, and conclude that equation. So do keep in mind the equations might not be explicitly given. You might have to deduce them from other givens. But anyway, nevertheless, let's see here. We have our equation, and my little personal ritual here, because I am easily confused. I had them backwards, or I got distracted. So easy to happen, right? I always remind myself, once I've identified the point and the curve and the equation, I like to remind myself, what am I looking for? Right? And the whole purpose of this whole business is I'm thinking now about the range of values of y over my given x slice. And so what I am looking for here is a y bound. I want to find in this equation, how can I write y as a function of x? And it's a very easy function of x. Y, solving for y and writing it in terms of x, is just x. Gotta love it. Everybody happy? All right, and then everything from there is plug and chug. Feels a little different. Let me erase so I can come back to here. Feels a little bit different because when you plug in these bounds into the, as you evaluate that integral, you're plugging in the 0 and the x into the antiderivative. It feels strange to be plugging in a function of x in for y. But it's not a problem. X, of course, is a constant. X is the outside variable. So it's going to feel a little weird. It's perfectly fine. Nothing to worry about. All right, let me pause. We've got many, many more examples coming. But real quick, pause. Does anybody have any questions on this example here? Yeah.
Since, so for the y1 value, are you always, I guess just one thing that throws me off is that it's kind of like y equals x for the whole duration from 0 to 1. So, like, I get that you can't put x as the upper and lower bounds because
Correct.
That just doesn't work.
That's right.
So how do you know to put 0 certainly for like,
Yeah, no, you've got to draw the picture. So for example, so we agreed that x is going from 0 to 1, and I've got this. These are what all my x slices look like, right? So the process is to fix one of those x slices. So we're going to fix that value of x, let's say, right? And real quick and dirty, that curve right there is where the lower bounds come from, and on those lower bounds, y is always 0. Yeah. So it's just the picture, right? I'm literally looking at the picture. I'm looking at the x slice. I have to be able to draw and see the x slice, and then that is what tells me where's my lower bound, and then correspondingly, let's see here. Oh, good color choice. Okay, I'll use this. This curve here is where my upper bound is going to be. And so that, again, gives me that upper bound. Does that make sense?
So just have one fixed and have one as a function.
The outside variable is fixed. The inside variables are going to be, the inside variable is going to have bounds that are functions. They're going to always be functions. They might be constant functions. That's a peculiarity. Don't count on it. But they will be functions of the outside variable.
Okay, so for like another example, it might be a function for both the upper and the lower.
Yeah, of course. That's going to be that's usually.
Okay.
Yeah, I'm starting with an easy example.
Okay.
Yeah, that's right. Yeah.
It just threw me off because it was a function for the whole time, so you're supposed to manually start at 0.
Yeah. I mean, you start wherever the x slice starts, right? The x slice here happens to start on the x-axis. That's not to be assumed, right? So notice I didn't say this is always 0. Of course it's not, right? The point is that this slice starts at that point. That point is on a certain curve. That curve has an equation. That's the process. The fact that it's on the x-axis is a peculiarity of this one example. Does that make sense?
Yeah.
Yeah. Okay. Yes.
Could you also do like the bound for like x to 1, or is that like a different thing?
That's a very different thing. So let's just write that down. So if we are looking at this value of x, right, and then now let's think about what would happen if y went from x to 1. Well, here's where y is equal to x, and there is where y is equal to 1. So that would give you, that would suggest that your x slice was like this. And if that were the case for all values of x, then you'd be basically tracing out that domain up there, which is just not what we're looking at. Does that make sense? Yeah, no worries. Everybody good? Many more examples to come. Let's see the next example. The next example is, in fact, the same example, just slicing in the other direction. And this may be possibly what you were thinking of. But here's same exact shape. Now let's just do our y slicing on the outside, a.k.a. first in the slicing process. So a little bit different. Now y goes from 0 to 1. these now are what my outside y slices look like. Right? So we're going to fix now a value of y between 0 and 1. We're going to fix y, let's say, I don't know, there. Right? This is what my y slice looks like. And now, again, thanks for the picture. It's all about the picture. The picture tells all. Don't try to do this without a picture, please. It's super dangerous. You'll get wrong answers practically all the time. Right? So the picture tells me this is my y slice for this value of arbitrary value of y. And okay, let's play the game. Here in my x slicing process, there's the first value of x. That's the point. That's the curve. That's the equation. Now, again, pause. It's real easy to lose track of what's going on here. Remind ourselves what we're doing. Why am I interested in this point? I'm interested in this point because it's a starting value for x. So I need in this equation now to solve for x as a function of y. And x as a function of y is that function of y. X is y. Does that make sense? Okay. And then let's see here the upper bound now for x. For my y slice, same y slice, that point is where x ends, going through my x slice. That's on that curve, which has this equation. A quick reminder, I lose track of things so easily. Why am I doing this? Why am I interested in this point? I'm interested in this point because it's an ending value in a range of values for x. And so in this equation, I solve for x. And again, easy to do in this case. Real easy to solve for x. X is 1. Everybody on board? So follow the process. I know some of y'all have had some exposure to multivariable calculus in high schools. My experience with high school multivariable calculus courses is they are in the best of cases, thin. And in the worst of cases, they tell you algorithms to bypass the actual meaning, and specifically those algorithms cannot be trusted. They are wrong significantly. Right? So this idea that, oh yeah, you can just kind of look at the algebra and just kind of write it down. Just take algebra from the given in the question, and you copy that into the bound. That's going to be your inside bound. No, it isn't. You cannot trust that. That will give you wrong answers in some cases. So please, I emphasize, whatever little quick, convenient little stories you may have been told in high school multivariable classes, that's not going to work, very likely. So make sure to draw the picture. Make sure to understand what is this slicing process that you're doing. And reminder, all we're doing is looking, down on this picture where we're just slicing up our loaf of bread. That's it. Right? But make sure you think it through and see the picture and identify the right points and identify the right curves and solve for the right variable to determine those inside bounds. Okay, yeah?
Is there like a rule of thumb to know which is it easier to slice x?
That's a great question. My next examples are going to be all about exactly that question. It's a long story is the short answer. Okay, so let's dive into that. Here is an example. You can see I've done the same question two different ways. The question said to write this integral, this double integral, as an iterated integral. You notice I've got two answers here, same exact region. My two answers, just as you asked, one is dy dx, the other is dx dy. Let's think about first of all, I want to talk through the little tricky parts of how I found these bounds. And then I want to address the question of which one of these do we like better? And secondly, how can I anticipate in advance so that I don't have to actually write them both down before I pick? How can I, guide myself in a good direction? Okay, so first the little tricky little particulars. Where did I get this negative 2? Negative 2. Oh, come on, pen. Negative 2 to 2. Where did I get that from? More to the point, let's start with the 2. Where did I get that? Well, I'm looking at my x slices. My x slices look like this. And I see that they start and end. Well, let's focus on the ending. X ends at that point. And that point's on a couple of curves, as it turns out. It's on this curve that has that equation. It is also on that curve that has that equation. And so I find that too by, as usual, solving for x in this now pair of equations. So you know y is x squared, you know y is 4. You got to put those together and figure out how you can solve for x. And it's not hard, of course, in this case. Pretty easy. But that's how you get this 2. Whoopsie, wrong color. That's how you get this 2. That is that upper bound. Nothing too crazy there. What's a little confusing is then the question comes up, okay, well, fine. Well, how do I find this lower bound for x? And you notice that that's going to come from that point, which is on the exact same 2 curves, which I think I'm coloring backwards, but I'm sorry. Doesn't matter. Okay, exact same 2 curves. So what's going on there? And the purpose that I want to point out here is to don't be too quick with your algebra, right? So looking at this right here, it's tempting to say, oh yeah, x is the square root of 4, which of course is 2. Not so. Again, remember x squared, the squaring function is not invertible. So you can't just say, oh, the square root. No, there are 2 square roots, right? And you have to think through which one is the one that I actually want in this case. And don't rely on the algebra to tell you. That's a bad strategy. I can manufacture cases where that will lead you wrong, right? What you want to do is rely on the picture. So in this case, when I solve for x and I get plus or minus 2, and I can see from the picture that, well, there's a plus 2 and there's a minus 2, but from the picture I can clearly see the one I'm looking for as my upper bound is clearly positive, right? It's clearly to the right of the y-axis, and so I pick the positive one because the picture tells me to. Does that make sense? Everybody happy, right? And then when you find yourself looking at the exact same algebra to find your lower bound, how do I know if the lower bound is going to be the plus or the minus? Well, again, thank you, picture. The picture is what shows me, well, that lower bound is clearly to the left there. So you pick the negative for the lower bound. So think it through. Rely on the picture. Very, very important. Okay, the other little thing I want to point out, looking at this other slicing process where we've sliced first perpendicular to the y-axis. Our y slices look like this, right? On one of which, for a given value of y, we're going to have a starting value of x and an ending value of x that are going to give us our bounds. And in both cases, those points are on the same curve. Right? So again, a little bit weird. And how do you know which one goes where? Same exact point. Right? Don't solve this for x too quickly and say square root of y. It's not so. It could be square root of y, but it also could be negative square root of y. So when you solve this equation, you get 2 options. When you're looking at the upper bound, let the picture tell you which one you need. When you're looking for the lower bound, let the picture tell you which one you need. Don't just rely on the algebra. You will get wrong answers. It's going to happen. Okay. All right. So that's the little particulars. Now let's look at what we've got as our results. Again, we're trying to write that double integral. Presumably we're trying to solve some problem. Presumably we want an answer. So our iterated integral options are going to be these two things here, and which one would we rather evaluate? And now, pros and cons. I don't know what this f is, so that would probably make some difference in the choice. But most of the time, I want this one here, because I don't like square roots. Right? Flashback to single variable calculus class when you had to do integrals that had square roots in them. Ugh. Right? Bad. Now you may be thinking to yourself, hey, no sweat. This inside integral, for example, it's just the bounds. All the work of the integration is going to come from this f function, and once I've done the anti-differentiation, plugging in stuff is not hard. True. The inside integral, though, is not the one you need to worry about. The one you need to worry about is the outside integral. You're going to have to take a y anti-partial of whatever this purple integral turns out to be. It's going to have square roots in it. I mean, I don't know what f is. Again, it's possible they might cancel very conveniently. You might get lucky. But you would expect, generically, that these square roots that you plug in at the very end for this inside purple integral, they're going to still be there. And that means your dy integral is going to have square root of y peppered liberally throughout that integrand. And again, nobody wants that. All exceptions granted, but generally speaking, that's not good. Okay, so I hope we're comfortable with why I think this is the good option and why I think this is the bad option. Now, how do you tell the difference in advance? Hopefully, fingers crossed, we don't have to actually write them both down every single time. I can't prove that the following result will always give you the right answer, but here's what I suggest most of the time will lead you well. And that is, keep in mind, when you choose an inside and an outside variable, you're effectively choosing which one of these variables do I want to have to solve for. Right? As I have it written here, this says I'm going to need to solve for y as a function of x. And so you look at your equation and you ask yourself, how would I feel about solving for y as a function of x? And how do I feel about the result that I would get? And how do I feel about that result, again, showing up a lot in my outside integral? Polynomial, not bad. I like constants better, right? But I mean, in this situation, that's not that bad of an option. Whereas, looking at this arrangement down here, how would I feel about having to solve for x in that equation? Not happy. That's where the square roots come from. It comes right from the fact that I have to solve for my inside variable as a function of my outside variable. I have to solve for x in this case as a function of y, and that's where the square root nastiness comes from. So, roughly speaking then, my little hack, little rule of thumb is identify which variable you would rather solve for and put that on the inside. Because you're going to have to solve for it, right? So, that's just a strategy. Okay. All righty. So now let's look at the, this is not my only criterion, by the way. So another example, and just different kinds of ugliness that can come up. Starting with, well, again, we have a certain domain. We're going to look at it twice. We're going to slice it up in two different ways, get two different answers, and we're going to decide which one we like better. So, okay, how broad strokes, details for y'all to check on your own. But with y going from 0 to 1 and looking at the y slices correspondingly, my lower bound comes from this curve, and my upper bound comes from that curve. And those are easy curves. Cool, no problem, all's good, reasonable result, not scared of it. Let's look at our other option. Our other option, we're slicing, you can see, with x's on the outside. Okay, tempting to say x varies along like so. here's the problem. While my lower bound for y always comes from that curve, which is easy, no sweat, no issue. Oh man, my upper bound comes from this curve. You can just watch those upper bounds as you go along. They come from that upper curve, and I can't write down an equation for that upper curve because it's kind of two curves, isn't it? Right? It's the one curve on the left. It's this other curve. It's got these. Well, I have to treat these cases separately. It's maddening, right? And this is what the result will be. We will look. Let's see here. We will look first at x going from 0 to 1. For those values of x, my lower bound for x comes from that curve. My upper bound for y comes from that curve. All's well and good. But then for this range of values of x, from 1 to 2, now still the same it's still the same sort of lower bound for y curve, but now notice this is where I sort of pass through that corner, and it's then a different curve with a different equation that gives me a different upper bound for y. And I can, algebraically I have to write that as two separate integrals. So now, which would you rather? Would you rather work out one iterated integral or two iterated integrals? I have a strong preference here, right? Weird, anomalous counterexamples granted, sure. But generally speaking, I want to do the one. I don't want to do twice the work. Right? So again, we have a clear preference, and again we ask ourselves the question, how can I anticipate this in advance? How can I see this coming and therefore avoid it in the first place? And my general strategy on this, and again, just for kind of, intuitive, convenient purposes, as you slice on the outside, there's for example, my putting y on the outside, there's my y range, and here's my y slices. Notice in that y slicing, I didn't slice through any corners. That's going to be the big giveaway. No corners. My first slice starts at a corner, but okay, no problem. In the middle of my integral, I'm not hitting any corners. At the end, I hit a corner. Yeah, okay, that's also not a problem. In the middle of the slicing process, no corners. Whereas, going in this other direction, slicing in the x direction, right? Looking at these x slices, I slice through a corner. Right? And that corner is where my upper bound curve for the y integral goes, sort of jumps from the one curve to the other curve, and that's why I have to stop the integral I had been working on, start a whole new one. It's because I sliced through a corner, loosely speaking, right in the middle of my x slicing process. Sliced through a corner. So the generally good guidance advice on this is try not to slice through corners. Simple as that. Yeah.
So on the second integral, you're integrating from right to left, right? Because you're starting at 0 and going backwards.
Are you talking about down here?
Yeah.
Okay. So I'm going left to right in the sense that x starts at 0 and ends at 2. So I'm going that way.
Okay. In terms of y, you're going from 0 to above. Oh, okay, I see.
Well, y is the stuff on the inside, right? And that's what I'm trying to avoid having to sort of, work through. But just as you imagine this x slicing process, what my keep in mind, x slices are perpendicular to the x-axis, right?
Yep.
So as I go through my x slicing process is when I slice through that corner. And I kind of know something bad's going to happen there. It's because of that, in other words, that this turns into that. It's because of that corner. Is that cool?
Yeah.
Yeah. Okay, so a couple of bits of advice that most of the time, if they come up at all, will tend to advise in the same direction. But there are some scenarios where there's really no corners to worry about, and it's the functions and which one's easier to solve for that you want to focus on. Sometimes the functions are all easy, but it's the corners that will be the giveaway that will, guide you in the right direction. So it's rare that these conflict with each other, but it's routine for only one of them to be relevant. And of course, sometimes they'll both be relevant. Okay. All right. Okay, next example. Sometimes you have to do a little bit more legwork to find the domain itself. Sometimes the domain's just not explicitly given. So here's an example for this. If I want to find the volume between this paraboloid, right, and this plane, and the volume between, you can see, is this region that I have shaded in gray down there. That's what's between these two surfaces. How am I going to find that volume? Again, notice the picture. Essential, right? You really need the picture to be able to see what is this thing I'm looking at all. Okay. So that noted, real quick kind of phase one part of the problem. I'm going to break up the volume into a bunch of little French fries, again, as usual, right? The volume, total volume is the sum of the volumes of the French fries. In any particular French fry, not too hard to persuade yourself that height is the difference of those z coordinates, right? And then the area of the base, you imagine there's a little rectangular little base there, which of course is the same as a little piece of area down there. So the area of the base is just going to be our dA. Delta x, delta y, slicing, blah, blah. But when using double integral notation, it's just going to be dA in the end. So it's fine to just start with that. So that's the phase one part of the problem. Now question, what is my domain for this integral? And I said differently, over what set are these points that tell me where my little pieces of area are? Over what set is that ranging? And again, a peel from the picture, it's going to be this shaded gray region down here that I'm highlighting in orange right there. So there's my domain. It was not given. I still actually don't know enough information about it, right? So how am I going to understand that domain? Now let me show you the wrong answer first. What a lot of students will do, this is complete nonsense, makes no sense at all. A lot of students will observe correctly that we're looking for that curve, which is the shadow of that curve, which is the intersection of these two surfaces. That's right, that's where this paraboloid intersects with this plane. So a lot of students will correctly reason that, I guess I want to find the values of x and y where both of these equations are happy. Right? And the mistake that they make comes in with how to solve. And it's easy to again sort of not look carefully enough at the algebra and how algebra works and think about the details. And a lot of say, I have two equations. I want to know when they're both true. And so a lot of students will do what they call setting the equations equal to each other. And they will set this equal to that and then try to solve. And I claim that's absolute nonsense. It is absolute 100% meaningless garbage nonsense. Doesn't do a thing. Now let me try to persuade you why. First of all, a plausibility check. I'm not sure if I've ever heard a mathematician say the phrase setting equations equal to each other, right? That's one thing. But here's an example, just for comparison purposes, just to make the preposterous a little bit more clearly preposterous. If I were to ask, where are these two equations both true, how would I solve and find when these are both true? Would it be reasonable for me to set that equation equal to this equation, observe that 3 is never 7, and then assert that these two equations can't both be true at the same time? Silly. Right? Does that make sense? So logically speaking, this makes the same amount of sense as that. So doesn't make any sense at all. Let me show you the right way to think about this, or a valid way to think about this. And that is, what we're looking for are values of x and y. Let's see here. Let me get to the... values of x and y. Points on the curve in question, in other words. Where the z distance that I go up to get onto the paraboloid and the z distance that I go up to get onto the plane, I need those two distances to be equal. Right? So I'm looking for where the green height and the blue height are the same. So I'm looking for where this and that are equal. So said differently, I need to solve for z in the first equation. Cool, already done. Sweet. Sometimes the fish jump in the boat. Then I also have to solve for z in this equation. Not already done for me. I have to do that part. Right? I have to, as the person solving this problem, you have to identify that you need to solve for that z. And those are the two things that you need to be equal to each other. So zooming out, if I can get there we go. So I want to set the green z equal to that blue z, which you can see I've solved for it right there. There's solving for z in the blue equation. Set that equal to the green z, and this is what you want to play with. I'm setting two things equal that, per the geometry, should in fact be equal. And what it gets you down to is an equation, which you'll notice quickly is the equation of a circle. A little bit annoying in the algebra. There's some fractions that come up. Nobody likes that. You'll also notice, again, figuring prominently, completing the square. Now, remember I made a pitch some time ago that that's a little bit of algebra that gets underappreciated in high schools, right? Got to make sure that you're good with completing the square. And that together, and there's your domain. Everybody good? All right. Okay, we're going to do one last thing. We have just finished section 5.2. We are now going to, in the remaining 2 minutes, we're going to finish section 5.3. Believe it or not, it's the quickest section in the book. There's hardly anything going on. It's just a trick. There's one little trick. And sometimes you might find yourself needing to compute something like this. How would you do it? You notice quickly that you're looking at an antiderivative of e to the x squared with respect to x, and you may recall that you can't do that integral in what they call closed form, in other words, without power series. How can you do that? You can't do the integral in the first place. It seems like we're dead in the water. The clever trick is simply to observe that this iterated integral actually comes from a double integral over a domain, and you can just draw the domain. That double integral over that domain, you can reslice in the other direction. You do your x slicing on the outside, 0 to 1. You then, for a given value of x, notice that y now goes from 0 to x. And clever little tricky thing that happens now, at a quick glance, it looks like there's no help. I mean, we still have, right here, you see the same problem that e to the x squared is our integrand. We're still, but you can't integrate e to the x squared, but you can in this case, because the inside variable is now y, not x. So this is not the world's scariest integrand. This is, in fact, a great big constant, because x is the outside variable. That means x is a constant, and it's super easy to integrate. And then the actual x integral that you end up looking at is doable with a substitution. So it's a really clever little trick. I think it's weird that it gets an entire section of the book when, in fact, really the big idea is just this one example. Y'all have a good rest of your Monday. See you later. Okay, let's see here.